Hello trig class, we're going to go over the sum and difference formulas in this video. So we're going to learn how to use the sum and difference formulas to find exact values of values that are not on the unit circle. So we're going to see the first addition to our special angles. Multiples of 30 have always been kind of like the lowest we could do, but now we can bring in some new ones because of these new formulas. Alright, when we are dealing with the sum or difference of a cosine function, I want you to pay particular attention to this. You're not going to have access to this on your midterm or your final. You need to know this. So if you look, cosine of the sum or difference, meaning we're adding two different angles together inside the cosine function, adding or subtracting them. But what I want you to see here is we are multiplying the cosine of the two angles together, multiplying the sine of the two angles together, and then either adding those or subtracting those. All right, when it is cosine, the cosines are together, the sines are together, okay? But then we change the sign in the middle. So if it's plus inside the cosine function, it becomes minus when we use the sum formula. If it is minus, then we are using plus. All right, and that comes from the fact that you can think of minus beta, minus the second angle, as plus negative beta. So everywhere there's a beta, we replace it with negative beta. And the cosine of negative beta is the same as the cosine of beta, so that wouldn't change. But the sine of negative beta, if you remember our odd properties, that comes out and it would change that from plus to a minus. It does change the sign. So you can actually think of these as just one formula, the top one. It just happens to be when beta is negative, it makes us change the sign in the middle there. All right, let's see how we can use these with some exact values. So we're going to find the exact value of the cosine of 105 degrees. 105 is not on the unit circle. If you look at the unit circle, there's 90 degrees, obviously right there to the positive y-axis, but if I rotated beyond that, if I went all the way to the next special angle that we had, that was 30 degrees and beyond that. It was 120 degrees. And that's where we found the next special value on our unit circle. So 105 degrees is less than that. So what can we do? Well, we can use the sum formula. So we're going to rewrite cosine of 105 as 45 plus 60. Right? And so now we are going to use the sum formula. We're going to use that top formula right there. It's the cosine of the sum of two angles. So now we can apply that formula. Cosine of 45, cosine 60 minus, again because it's plus on cosine, we switch it to minus, the sine of 45 times the sine of 60. All right, when the angle is, or when the function is cosine, we're adding in there. It's cosine, cosine, sine, sine. Same, change the sign, okay? So cosine of 45 is square root of 2 over 2. Cosine of 60 is a half. Sine of 45 is also the square root of 2 over 2. And the sine of 60 is the square root of 3 over 2. All right, now when we have the same denominators like this, we're just going to multiply the fractions together. 2 times the denominators, 2 times 2 is 4. 2 times 2 is 4. But when we have a radical and not a radical, we can't combine those. We just put the number that's out in front of the radical. So that would be like 1 square root of 2 over 2 times 2 is 4. And then the square root of 2 times the square root of 3 is the square root of 6. So that's minus the square root of 6 over 4. All right, and now you cannot combine the values under the radical. I can't say that's the square root of negative 4 or something. So I would just have to combine it into square root of 2 minus the square root of 6 over that common denominator of 4. So that's where that last line is coming from. It's just multiplying the numerators together, multiplying the denominators together, but once you have that common denominator, remember you just combine the numerators. All right, they factor out the 1/4. You can leave it in there. It's either way is fine. All right, same thing for radian measures. You just have to come up with two angles that add to the angle that you're given. Add or subtract. It doesn't have to be addition. All right, notice that pi over 6, that is a special angle. Pi over 4 is a special angle. So pi over 6 plus pi over 4, with getting a common denominator, would become 5 pi over 12. All right, so you can come up with different combinations of the special angles on the unit circle to come up with these angle measures in this section. So I'm going to look for, again, the pi over 6, pi over 4. I'm going to be using the x and y coordinates there in the calculation. I just got to make sure I get everything in its right place. So again, cosine on the outside, sum on the inside. That's going to be cosine cosine minus sine sine. So we're keeping the two angles together, the pi over 6, pi over 4. The first time both inside cosine, the second time both inside a sine function. All right, again, same numbers that we saw before, the square roots of 3's and the square roots of 2, just different combinations because we're dealing with slightly different angles here. But same number that we're seeing, right? It's just the square root of 6 minus the square root of 2 this time, instead of the square root of 2 minus the square root of 6. It's all just about the order that the multiplication comes in. But you're going to see a lot of these, just like we saw the square root of 3 over 2, the square root of 2 over 2, those same numbers before. When we're dealing with multiples of 15 degrees now, we're going to see numbers like this, the square root of 6 minus the square root of 2 divided by 4. Right, there's those odd cofunction identities, right? The cosine and sine are cofunction identities. So they are equal when they when we have the output of the sine function or the cosine function. It's equal to the output of the cofunction with the input being subtracted from pi over 2. So what I mean by that is the input here is theta. We're subtracting theta from pi over 2. And that we get the exact same output. It's equal if we take the cofunction of this. All right. This would also be the same if this was secant theta and the cosecant of pi over 2 minus theta. All right. And it would be the same if it were the tangent equal to the cotangent of theta. So these are all cofunction identities. And we can now show that they're true because we have the difference formula. All right, now when our sum or difference is inside the sine function, it's a little different now. Instead of it being cosine, cosine, sine, sine, it is now either a sine and a cosine together, cosine and sine together. So now it's the sine of one angle and the cosine of the other. The cosine, we switch. Now sine had alpha, now cosine has alpha. Cosine had beta, now sine has beta. So instead of cosine, cosine, sine, sine, now it's a sine and a cosine and a sine. All right, the other thing to get down is when it's sine, we don't change the sign between the expressions. So when it's plus, we add. When it's a minus, we subtract. So cosine, it stays the same trig function, cosine, cosine, sine, sine. And then it changes the sign of the plus or minus. But sine keeps the sign of the plus or minus, but it changes trig functions from one group to the next. All right, find the exact value of the sine of pi over 12. Now, pi over 12, again, is not on the unit circle. Pi over 6 is the smallest angle we see on the unit circle. This is half of that. But we can get pi over 12 if we subtract 3 pi over 12, which is pi over 4, minus 2 pi over 12, which is pi over 6. So we can get this from, again, special angles that we do see. All of these that you see in this section should be something that you can derive from the special angles on the unit circle. All right, so we're going to use a difference formula. We got sine, so we need a sine and a cosine, and then we switch. Okay, so we start off with the sign of the number before the minus sign. There's my minus sign, so sine gets that number before the minus sign. Cosine gets the other number. Then we switch it, or we keep the minus. That's like that minus that we're seeing right there. And then we switch who has pi over 4 and who has pi over 6. So like these angles switch places. So pi over 6 goes from being inside a cosine to now being inside a sine, and vice versa. Pi over 4 switches over to cosine. All right, once again, we've seen these angles before, so we're going to get those same numbers that we've been seeing. We're going to see the square root of 2, the square root of 3, and then in the denominator we're going to see 2's. So there's that number again. So sine of pi over 12, we're getting the same thing that we got from the cosine of 5 pi over 12. All right, now looking at this, 75 and 15 degrees, not special angles. But when I'm seeing sines multiplied by cosines, switching around, like the 75 and the 15 are switching places in the next expression, we're adding or subtracting, that's a sum or difference of sines. So it's because it's one sine, one cosine, that's the sine. All right, and because this is a plus between them, we're adding the two angles that we're given, 15 and 75. So that's the way we look at it when we're going back the other way. We're basically taking the expanded sum formula and breaking it back down into what were the two angles that were added together inside the sine function. So that means we just add those together, get 90 degrees, and then the sine of 90 degrees is 1. Alright, just a quick thing to show you. I'm going to switch over to degree mode just for a brief second to do this example. Alright, your calculator can handle this. You just got to make sure you close these parentheses off. So I'm going to put in a 75. And when I got all the expression in there, I just hit enter, and it shows me that it's equal to 1. So it's not going to simplify it for you. You're not going to switch it to the sine of 90, but it does evaluate it. So you can definitely check your work with this. Alright, now let's look at an example that is having us do a little bit beyond what we've been seeing, just plugging into a formula. Now we got to do some thinking. So we're told the sine is 1 over the square root of 2. That's the same as the square root of 2 over 2. Okay, so they can give you any version of these, and you need to know what to do with it. Alright, we're told here the angle measure is between pi over 2 and pi. Recall in a unit circle, that would imply we're in quadrant 2. Right, there's pi over 2, there's pi, and we're somewhere in here. So that's where this angle is. So that means we're in quadrant 2. Right? That's important because that'll let us know cosine is going to be negative, right? If we're in that value. Alright, sine of beta is negative 1/3. Sine's the y-coordinate, so I know that I've got to be in quadrant 3 or quadrant 4. I have to be in one of those two quadrants for sine to be negative. Remember, sine is the y-coordinate. The y-coordinate's negative means we're down here somewhere. Alright, the angle beta is between pi and 3 pi over 2. There's pi again. 3 pi over 2 is down here on the negative y-axis. So angle beta is down here in quadrant 3. Right. The reason why this is so important is because when we multiply these angles together in the formula for part C and D, we need to know what the sine and cosine are in these quadrants when we're doing this. All right, 1 over the square root of 2, if sine is 1 over the square root of 2, cosine is plus or minus 1 over the square root of 2, or the square root of 2 over 2, because remember that happens at all these 45-degree angles. That's where we find sine and cosine being the square root of 2 over 2. So we know we're going to be in that for that second quadrant at the 45 degree there, so the 135 degrees, or again, 3 pi over 4 radians. So cosine is going to be, because again in quadrant 2, in this quadrant, cosine is negative. That's going to be negative square root of 2 over 2. Right, the cosine of beta, we can't just, it's the negative 1/3, that is not a special angle for sine. So I'm going to need to use that Pythagorean identity for cosine. 1 minus sine squared beta. That's what cosine squared beta is. Alright, so 1 minus sine of beta is negative 1/3. We square that, we'll get 1 minus 1/9 is 8/9. That's cosine squared. So taking the square root of that, I get plus and minus the square root of 8 over plus and minus the square root of 9, which is 3. And then 8 can be simplified. That should be plus and minus. The square root of 8 is the square root of 4 times 2, and the square root of 4 is 2. So I would write this as 2 square root of 2 over 3. Now which one is it? Is it plus? Is it minus? Well, beta in this quadrant, cosine is still to the left. Alright, we're still having to go left to get down to quadrant 3. So that means this is the negative 2 square root of 2 over 3. It's cosine beta. So there's cosine alpha, there's cosine beta. Alright, cosine alpha plus beta. That's cosine alpha, cosine beta. Remember, cosine is cosine cosine. Change your sign, minus sine sine. Sine alpha, sine beta. Alright, so we know from the previous problem, cosine alpha is the square root of 2 over 2. Cosine beta is cosine beta was negative 2 square root of 2 over 3 minus, and now the sine alpha that was given to us, that was square root of 2 over 2. The sine of beta was negative 1/3. That was also given to us. Multiplying the top, I got a square root of 2 times the square root of 2, that's 2. There's another 2 there, that would be 4. Negative times a negative is a positive 4 over 2 times 3 is 6. Alright, then we have a negative here, we got a negative here, that's a plus. Square root of 2 times 1 is the square root of 2. 2 times 3 is 6. So I can write this as 4 plus square root of 2 over 6. Alright, you could also divide the 4 by 6 and get 2/3 plus the square root of 2 over 6, but I like to write it just to combine it into a single fraction like that. Alright, now when we switch this to sine, remember it's sine alpha cosine beta. We get a sine and a cosine in each part. We keep the sign this time though. Instead of switching it to a minus, we keep the plus. And now we switch. So in the first one, alpha was inside of sine, so now alpha is going to be inside of cosine. Before beta was inside cosine, now beta is going to be inside of sine. Sine of alpha was given to us, that was square root of 2 over 2. The cosine of beta was that negative 2 square root of 2 over 3. All right, plus the cosine of alpha, again that was this negative square root of 2 from part A. The sine of beta was given to us, that was the negative 1/3. All right, I got a square root of 2, another square root of 2, that'll be 2. Times negative 2 will be a negative 4 over 6. Square root of 2 times negative square root of 2 times a negative 1, that'll be a plus square root of 2 over 6. All right, so I can write this as square root of 2 minus 4 over 6 is how I would write that. So knowing what quadrant you're in is very important for when we find the values for A and B here, the cosines. And then we just plug in the formula into the sum or difference formula and just make sure you got your signs right. That's everything for these questions. All right, remember when we are doing the identities, we can't add, subtract thing from both sides, meaning I couldn't subtract 1 from both sides of this equation. I have to work with one side at a time. So what I'm going to do, if I see a sum or difference inside a trig function, that's usually telling me that that's where you're going to go, especially in this homework set. But when I'm splitting this up, I'm going to use that sum or difference formula, in this case the difference formula for cosine, break that up, and then I see here addition in the numerator, so I can break this into two fractions. One with this over the sine alpha sine beta, and one with this, which is the exact same thing, over sine alpha sine beta. And that is, you can probably tell, going to move us towards that identity. So splitting into two fractions, that's a very common thing to do when verifying identities if you have a plus or minus up top. And then notice here, cosine alpha divided by sine alpha, that's cotangent alpha. Cosine beta over sine beta, that is cotangent beta. And then here everything is the same, it all cancels. And because it's all canceling, we're just going to get 1 there. And that establishes the identity. That is the right hand side. So we've done what we're asked to do. Alright, notice the little slight variation between the tangent function. It's the location of the plus and the minus. So for tangent alpha plus beta, we're adding inside the tangent function. Notice up top I got tangent alpha plus tangent beta. It almost looks like we're distributing. We're not distributing, but it kind of looks like that. But in the bottom we change the sign. It becomes a minus sign, and now we're multiplying instead of adding. So just be careful with the operations and the signs. You got to get this down so for when you do it on the midterm. Right? When it's tangent subtraction, when we're subtracting inside the tangent, again, think of it like distributive property tangent alpha minus tangent beta in the numerator, and then we change the sign when we do the 1 and the multiplication between the two. All right, once again, if I'm doing an identity and I see the tangent of something plus something, I'm using that top formula there. So I'm going to use formula number 6, tangent alpha plus tangent pi, and then 1, because it's plus up top, 1 minus tangent alpha times tangent pi. All right, recall the tangent of pi is equal to 0. So right here, everywhere we're seeing tangent pi, it's been replaced with 0. So we're adding 0 to tangent, so we're just going to get tangent. But then we're multiplying 0 times tangent in the denominator. So we're just going to write that as 1 minus 0, which is just 1. So we have tangent plus 0, which is tangent, divided by 1 minus 0, which is 1. So tangent divided by 1 is just tangent. Once again, I have a sum inside the tangent on the left-hand side. I'm going to split that first up into the sine and cosine identities, and then use the sum formula for sine, sum formula for cosine. All right, recall at pi over 2. Remember, pi over 2 is one of those special angles on our unit circle. So pi over 2 is right here, same as 90 degrees. And at that point, I'll be at the point 0, 1. I'm on the y-axis. So the cosine of pi over 2 is 0. The sine of pi over 2 is 1. So in this formula, everywhere I see a cosine of pi over 2, that's going to go away, and we're multiplying. So all of this will go to 0. All of this will go to 0. So it's just everything in this problem comes down to this. All right, sine of pi over 2 is 1, so this is 1. This is also 1. So this is just positive cosine divided by negative sine, which is just the negative cotangent. Alright, so again, you are not going to have a unit circle on this test. I strongly encourage you, if you haven't already watched the video on how to make a unit circle, watch that, get that down. That needs to be the first thing you do when you take your midterm. Draw that unit circle. Alright, we want to find the exact value of the sine of this crazy looking combination of inverse trig functions. Don't fret when you see something like this. Don't completely freak out. Just take your time, take a deep breath. I've told you guys before that the inverse trig functions are just angles. This is like alpha, and this is another angle, inverse trig function. So this is like beta. So this is like the sine of alpha plus beta. Alright, so we're going to use the sum formula for sine. This is sine alpha cosine beta. Alright, because it's a plus between them, I'll subtract I'll keep the same. Subtract for cosine, keep the same for sine, and then switch the order so it becomes cosine alpha sine beta. Now if alpha is the inverse cosine of a half, then the cosine of alpha equals a half. So right there I can replace that with a half. If the angle beta is the inverse sine of 3/5, then the sine of beta equals 3/5. So that means this part right here is 3/5. Now we need sine of alpha and cosine of beta. We need the other angles. We can use the Pythagorean identities to give us these other angles. Alright, so sine is the square root of 1 minus cosine squared. Alpha was a half, so squaring cosine of alpha was a half. So squaring that would give me a fourth. 1 minus a fourth is 3/4, and the square root of 3 is not a perfect square, but the square root of 4 is. So we can make that look like the square root of 3 over 2. So there's the sine of alpha. Alright, same thing for cosine of beta. I know the sine is 3/5 from before, so I'm going to square that. Squaring 3/5 gives me 9/25. 1 minus 9/25 is 16/25, and both 16 and 25 are perfect squares, so that becomes 4/5. And now I can plug in everything that I need back into the expression. So I had the 1/2 and the 3/5 from that cosine alpha sine beta, but now I know that the sine alpha is the square root of 3 over 2, cosine beta is 4/5, and I can combine that. Right, it's not the prettiest looking number, but it is the exact value of the sine of the sum of those two inverse trig functions. Alright, one of the last examples that you see in here is the example when we have a sine plus a cosine equal to 1. So this is a rare problem in which factoring, when we have these equations involving sines and cosines, trig functions, isn't possible. So what we end up doing is squaring both sides, and the reason we would want to do that is because we have sines, cosines, and 1s. And recall sine squared plus cosine squared equals 1. That's an identity that we could use if we had some of those in here to work with. So that's what I'm going to do here. I'm going to square, these two things are equal, so their squares will be equal. Right, but when you square, recall, you don't just square the sine and square the cosine. You got to FOIL this out and multiply it by itself. So sine plus cosine times itself. Sine times sine is sine squared, right? But we have an outside sine times cosine, that's sine cosine. And inside we have another cosine times sine. And then lastly we have a cosine times cosine, that is cosine squared. So we do get a sine squared and a cosine squared. We just also get this inner term. Right, sine squared plus cosine squared is 1. So I get 1 plus sine cosine is the same as cosine sine. So I have 2 sine theta. Alright, subtracting 1 from both sides, I mean 2 sine theta cosine theta is equal to 0. Now, when we do this, our goal usually, not always, but usually is to get some type of multiplication equal to 0. And I have that. I have 2 sine theta times cosine theta equals 0. So any piece being set equal to 0 could potentially solve this for us. So sine is equal to 0 when, again, in this region, when theta equals 0 or pi. Cosine is equal to 0 in this region when theta is equal to, not cosine theta, theta is equal to pi over 2 or 3 pi over 2. Right, and you may think you're done, but you have to check. Why? Anytime you square to solve, if you square an equation to solve, you have to check. Okay, and the reason is you could have something that's not true, like -3 is equal to 3. That's not true. But if I square both of these, now I get 9 is equal to 9. That is true. So after I square, I might get something that's true that back in the original was not true. So you always have to check these. So if I check theta being 0, I get the sine of 0 plus the cosine of 0 equals 1. And that's what we're supposed to get. Right? If I plug in pi though, I get the sine of pi, which is 0, plus the cosine of pi, which is not 0, or it's not 1, it's -1. And 0 plus -1 is -1, and we're supposed to get 1. That's not a solution. Why did it work? Because -1 squared is +1. 1 squared is +1. So that's why this is showing up when it's not supposed to be. Right? Pi over 2 works, but 3 pi over 2 does not. So we had 2 that were solutions and 2 that are referred to as extraneous solutions. They don't solve the original, but they do solve after we square. Only keep the ones that work when we check. All right, you can use a calculator to help you check. That'll be a really great tool to help you check these. Or your unit circle again when you have special angles like that.